All right, welcome to this video lesson on the quantitative relationships between the variables of pressure, volume, and temperature for a gas. We will see that we are going to put all three of these variables together into a math equation called the combined gas law. To do this, let's quickly review the relationships of each of the variables individually. Boyle's law says that if you increase the volume of a gas, you will decrease the pressure. This is known as an inverse relationship. And if we graphically sketch that out with volume, if you're intentionally changing the volume, the pressure will change as a result. So this relationship ends up looking like a downward falling curve. If we relate these two variables, because they are inversely related, if you multiply the pressure of a gas times its volume, and it's going to come out to some constant number. You could change the pressure to a new pressure, the result will be a new volume, but even when you multiply that new pressure and new volume together, you get a constant. So keeping that in mind, we're going to come back to how that factors in. Charles' law relates temperature and volume. If you increase the temperature, that increases the volume. Right? If we set it up graphically with temperature on the independent variable axis, we have a direct graph that looks like this. And this time the mathematic relationship, when you have a direct relationship, if you, instead of multiplying, if you divide the volume by the temperature, you will get a constant number. So in other words, if you have a gas at one temperature and volume, and you put those numbers into a fraction and divide them, it's going to get a constant. If you change that temperature to a new volume, taking that new temperature and that new volume and dividing them will give you the same constant. The third graph relates pressure and temperature. If you intentionally change temperature, the pressure will change as a result in a direct relationship, meaning as you increase the temperature, the pressure will also increase. This is a direct relationship. And again, mathematically, a direct relationship means if you take the two variables and divide them, no matter what new pressure or what new temperature it gets to, it will work out to be a constant. So we're going to be able to take advantage of that and put them together in what is called the combined gas law. And notice that we have pressure and volume on the numerators, right? So if we do pressure times volume, right, they're being multiplied up here, pressure times volume, and we have volume and pressure in the numerator of both of these fractions, we are going to put pressure and volume in the numerator. And we saw up here that temperature was in the denominator. So if we have pressure times volume and divide it by the temperature, that's going to be equal to a constant that will be equal to the pressure times the volume divided by the temperature when you change those conditions. So what we do is we're going to say P1 times V1 divided by T1 is equal to P2 times V2 divided by T2, where 1 is the initial condition and 2 is the new condition. All right, when will you use this? You will use it when the conditions of pressure, volume, or temperature are changing. If you get a word problem and it's talking about the pressure is changing or the volume is changing, then you know you are going to use this combined gas law. Okay. If we take a look at the reference tables, this is reference table T. This is reference table T. Right? And if you take a look, the combined gas law is listed there. So this is not an equation you have to memorize. You likely will because you'll use it enough that it's not too tricky. But know that it is there on reference table T. A note about the units. Pressure units for pressure 1 and pressure 2 must match. They must both be in atmospheres, or they must both be in kilopascals, or they must both be in millimeters of mercury. Doesn't matter, they just have to match so that they cancel. The volume units must also match. They can both be in liters or they can both be in milliliters. Either way, they have to match each other so that they will cancel. Temperature units must also match. However, this is important, and those temperature units must be in Kelvin. So if you are given a Celsius temperature, you are going to need to convert it to Kelvin. Of course, the equation for that is Kelvin is equal to Celsius plus 273 if you need to convert it. Now, interestingly enough, the temperature equation can also be found on your reference tables, reference table T. That is also there for your convenience. All right, so a note about best practices. Let me move the camera here so we can see this better. Right, so let's say we have a problem given to us. Let's work through what the best practices means. If you initially have a gas with a pressure of 84 kilopascals and a temperature of 308 Kelvin, and you heat it to a temperature of 616 Kelvin, what will the new pressure be? Assume the volume of the container is constant. So the first thing I recommend you do is make yourself a table. I've printed one here for convenience, but no big deal if you have to make one. It is definitely best practice to keep yourself organized. So what you need to do is figure out from the word problem, what's the first pressure? What's the initial pressure? Well, if you read through, you're going to see that it's 84 kilopascals. The initial volume is not listed, but that says that the volume of the container is constant. So what do you do if the variable is constant? We are going to just put a dash through there. It's not changing, so it's not going to affect our math. Continuing to make a table, the temperature was 308 K at the beginning. We're going to heat it to 616 Kelvin. So that's our new temperature, and we are being asked to find what the new pressure will be. So P2 is going to be our X. Okay. So we made a table. If something's not changing, we just ignore it. So let's see what that looks like with the equation, right? And so if we have the original equation, P1 V1 over T1 equals P2 V2 over T2, and we just found out that the volume 1 and volume 2 are not changing, we can just eliminate the V's. So the equation that we're really working with is P1 over T1. Sorry, I just realized you couldn't see it. P1 over T1 equals P2 over T2. So if a variable is constant, you remove it from the equation. Okay, now I'm going to put a big star here. Best practice is to rearrange this equation before you start doing any math. So rearranging the equation means to cross multiply and then solve for the variable you are looking for. Solve for the variable of interest. And I'm going to circle my variable of interest. We know that P2 is what we're trying to solve, so I'm going to circle it in my equation. And when I cross multiply, the first thing that happens is I get P1 times T2, right here, equals T1 times P2. Okay. I'm still going to circle P2 because I have not gotten it all by itself. So that's the next step. To get P2 all by itself, I have to divide both sides of the equation by T1. So P2 is now equal to P1 times T2 over T1. Okay, so P2, I'm going to rewrite it here for convenience. So P1, T2 over T1. So that's the equation I'm going to use. Now I can start plugging and chugging, meaning I can substitute my numbers in. So P1 is 84 kPa, and yes, you need to include the unit. I'm going to multiply that by T2, which is 616 Kelvin, and I'm going to divide that by T1, my first temperature, which was 308 Kelvin. I'm going to cancel units that can rightfully cancel. I recognize the only unit that doesn't cancel is KPA, so I know my final unit's going to be in KPA. And now it's a matter of bringing out my calculator. So 84 times 616 divided by 308. And we get 168 kilopascals. Okay, so that's how you work the best practices. Let's take a look at a couple problem types. Right? Basically, you're going to be asked to either solve for V2 or T2 or P2. Sometimes one of the variables will stay constant, and sometimes all three variables are changing. So let's take a look and see if we can't work through another one together. A gas has a volume of 800 milliliters at negative 23 degrees Celsius and 300 millimeters of mercury. So let's take a look. Our first pressure is 300 millimeters of mercury. The volume was 800.0 milliliters. The temperature was negative 23 degrees Celsius, but we are going to have to add 273 to that, right? So we got 23 negative plus 273. So our temperature here, our Kelvin temperature that we need to use for the math, is 250 Kelvin. Okay, let's see. What would... Yep, okay. Thought I did the math wrong there for a second. All right, so P2, what would the volume of the gas be at 227 degrees Celsius and 600 millimeters of mercury as our pressure? 600.0 millimeters of mercury is our new pressure. I noticed that my two pressure units match, so that's great. The new volume is what we are looking for. What would the volume of the gas be? So that's what we're looking for. T2 is 227 degrees Celsius. We have to add 273 to that. 227 plus 273, and we get 500 Kelvin. Okay, so that is the organization of our data. What we want to do here is start by writing our equation, P1 V1 over T1 equals P2 V2 over T2. When we cross multiply, well, first of all, before we cross multiply, I'm going to circle that I'm solving for V2. Cross multiply to solve for V2, we get P1 V1 times T2 is equal to T1 times P2 times V2. We've gotten rid of the denominator, but we still haven't solved for V2, so I have to divide both sides by T1 and P2. Okay, and so this is my plan for the math, right? That's my plan for the math. So I'm going to set this up over here. V2, P1, V1, T2. Again, I'm just setting it up so it becomes very clear. I'm articulating very clearly what my plan of action is for the math. Now I can start substituting numbers. P1 is 300.0 millimeters of mercury. V1 is 800.0 milliliters. T2 is 500 Kelvin. Okay. I'm going to divide that by T1, which in Kelvin is 250 Kelvin, multiplied by P2, which is 600.0 millimeters of mercury. Okay, I'm going to take notice of any units that cancel. So millimeters of mercury cancel. Kelvin cancels. The only unit I'm left with is milliliters, so I know that my final unit, my final answer will have a unit of milliliters. Now be careful with your calculator here. I see a lot of mistakes that students make when they go to divide when there's two numbers in the denominator. So my suggestion is to do all the multiplication in the numerator. So 300 times 800 times 500. Then I don't even need to hit the equal sign. I could, but I'm going to divide by 250, and I'm going to divide again by 600. I'm not using any parentheses. You're welcome to use parentheses, but I find that this is the fastest way in terms of keystroke entry. So what I see here is 800 milliliters is my final volume here. If we were to consider significant figures, our original temperatures had 3 and 4 significant figures, so I probably should have indicated that here that we have 3 sig figs in those temperatures, meaning our final answer has 800 point or 3 total sig figs. All right, let's take a look at this next one. This is an important, tricky one that I want you to process. If I have 2.9 liters of gas at a pressure of 5 atmospheres and a temperature of 50 degrees Celsius, I'm going to stop there because they have just given us our initial conditions. 2.9 liters, initial pressure is 5.0 atmospheres, the temperature is 50.0 degrees Celsius. I need to add 273 to that to get Kelvin. So 50 plus 273 is 323 Kelvin. What will be the temperature of the gas? That's going to be what we're solving for. If I decrease the volume to 2.4 liters and decrease the pressure to 3.0 atmospheres. So I notice my liters unit matches, my atmosphere unit matches. So now it's a matter of prepping the problem. P1 V1 over T1 equals P2 V2 over T2. This time I'm trying to solve for T2, and this is where it gets a little tricky because you're solving for a variable in the denominator, and this is where I see sometimes students make mistakes. So cross multiplying, I get P1 V1 times T2, doing that one first, doesn't matter, equals T1 P2 V2. I'm going to circle T2 to remember that that's what I am solving for. I want P1 and V1 to cancel out. So now I have my plan. I have T2 is equal to T1 P2 V2 over P1 V1. Okay, so that's my plan. Now I have to start plugging in numbers. T1 is 323 Kelvin. P2 is 3.0 atmospheres. V2 is 2.4 liters. P1, 5.0 atmospheres. V1, 2.9 liters. This is where I take a moment to cancel any units and recognize that my final unit of temperature should be Kelvin, which that makes sense, so I'm happy about that. Now it's a matter of doing the math. We've got 323 times 3 times 2.4 divided by 5 divided by 2.9. Final answer here is 160 Kelvin. All right. Hello, Yusuf. All right. All right, so here we go with our final answer of new temperature to be 160 Kelvin. Actually, I don't think we need to have a decimal there because 2 sig figs, 2 sig figs. All right, there you go. You have now learned how to use the combined gas law. See you back in the classroom.